Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen that what is programmable logic device, and we have also seen that how the ROM can be used as a programmable logic device. And we have seen that using this programmable ROM, it is possible to implement the different Boolean functions. So similarly, in the next couple of videos, we will learn about the two other programmable logic devices, that is PAL and the PLA. And in this specific video, we will learn about the PLA. So this PLA and the PL are slightly different from the PROM, and they have a certain advantages over the PROM in the certain applications. So let us see that. So we have seen that this programmable ROM has a fixed AND gate array and the programmable OR gate array. So we have seen that in this PROM, this decoder acts as a fixed AND gate array. And here, each AND gate output in the decoder represents the specific minterm. And we have seen that by making the interconnections between the input of the OR gate and the decoder, it is possible to implement the different logic functions. So in this PROM, for the given n number of inputs, since all the possible minterms are available, so it is possible to implement any functions with the n variables. And here, since all the minterms are readily available, so if we know the truth table of any logic circuit, then it can be easily implemented with this ROM. That means whenever we implement any logic circuit using the PROM, then there is no need to minimize the Boolean function. And therefore, when the ROM is used as a programmable logic device, then the design time for any given logic circuit is also short. So that is one of the advantage of the ROM. Now using this ROM as a programmable logic device is beneficial whenever we are using most of the minterms of the decoder. For example, if you take the case of the code converter, then during the design, we are using most of the minterms, or sometimes we are using all the minterms. But apart from these specific cases, when we are implementing any other logic circuits, then we are not using all the minterms, and the remaining minterms remains unutilized. For example, in the previous video, we have implemented the full adder and the full subtractor using this 8x4 ROM. So as you can see, the first two expressions are the difference and borrow outputs for the full subtractor, while the other two expressions are the sum and the carry output of the full adder. And this is the corresponding implementation using this PROM. So as you can see over here, in every output of the OR gate, we are not utilizing all the minterms. And in fact, if you see, then in all the 4 outputs, we are utilizing only 4 minterms. That means many times, while implementing the functions using the PROM, we are not utilizing full hardware resources. Of course, since all the minterms are available, so this PROM provides more flexibility, and it is possible to implement any functions of the n variables using this PROM. But most of the time, the full utilization of the hardware does not happen in this PROM. And here, since we are not minimizing the Boolean function, so even if there is a don't care conditions in the function, we cannot utilize them to minimize the Boolean function. Moreover, if you increase one input in the PROM, then the size of the ROM will also get doubled. For example, over here, if we increase the one more input in this 8x4 PROM, then we will require the 4 to 16 decoder in this PROM. And therefore, the size of the ROM will also become 16x4. That means just by adding the one input, the size of the ROM will become double. And after adding one more input, if we are not utilizing all the minterms, then it means that we are not utilizing full hardware capacity of this PROM. That means in the certain applications, to effectively utilize the available hardware resources, the other programmable logic devices like the PL and the PLA are used. So in this video, let us learn about the PLA. So this PLA stands for the Programmable Logic Array. So in this PLA, both AND array and the OR array are the programmable. So in the PROM we have seen that the AND array was the fixed one, while the OR array was the programmable. But in this case, both the arrays are the programmable. Now in the PROM, we have seen that if we have n inputs, then the total number of AND gates in this AND array will be equal to 2 to the power n. That means in the PROM, if we have n inputs, then the total number of product terms is equal to 2 to the power n. But in the PLA, for the n inputs, the total number of AND gates or the product terms is less than 2 to the power n. And then in this OR gate array, we can have the m number of OR gates. So here, the each OR gate output represents the one function. That means if we have a PLA with the OR gates, then it can implement total m different functions of the n variables, where the n is the number of inputs in the PLA. And here, the connection between the AND gate output and the OR gates are the programmable. So this is one of the example of the PLA. So as you can see, this PLA consists of the 3 inputs, and these 3 inputs are given through the buffer. So these buffers generates the true output as well as the complemented output. So internally if you see each buffer, then it consists of total 2 inverters. The one will generate the complemented output and the second one will generate the true output. So through these 3 buffers, total 6 inputs are generated, and these 6 inputs will go to the each AND gate. That means here, the each AND gate will have total 6 inputs. And of course, these inputs are the programmable. That means by programming, here we can decide which inputs will be connected to the AND gate. So we can say that here this AND gate array is the programmable. So by default if you see, then all the inputs are connected to the AND gate. So here, since the inputs and their complements are connected to the AND gate, so by default, the output of the AND gate will be equal to 0. For example, if both A and the A dash are connected to the AND gate, then as you know, this A dot A dash is equal to 0. So by default, the output of the AND gate will remain 0. But through programming, we can remove some of the interconnections and it is possible to implement the specific product term. So as you can see over here, in this specific PLA, we have total 5 AND gates. That means here, we can generate total 5 product terms. So if you compare it with the 3 input PROM, then it consists of the 3 to 8 decoder. And as you know, in this 3 to 8 decoder, we have total 8 AND gates. So compared to that, for the same number of inputs, the PLA has the less number of AND gates. That means in this PLA, the total number of product terms that we can generate is less than 2 to the power n. So in this PLA, we have total 2 OR gates. And in this PLA, since we have total 5 AND gates, so each OR gate will have total 5 inputs. And of course, these inputs to the OR gate are the programmable. That means in this PLA, both AND gate array and the OR gate array are the programmable. Now in many programmable logic arrays, it is possible to generate the output functions either in the true form or the complemented form. So in this case if you see, then the output of the OR gates are connected to the XOR gate, and one of the input to the XOR gate is the programmable. So by programming this input, it is possible to generate either true output or the complemented output. So whenever the one of the input to the XOR gate is 0, then it will generate the output in the true form, because as you know, this A XOR 0 is equal to A. Similarly, when this input is equal to 1, then it will generate the complemented output. So in this way, through programming, it is possible to generate the true output as well as the complemented output. And during the design, sometimes this feature is very useful. So once we take an example, then it will get clear to you. But here in this PLA, since the number of product terms that we can generate is limited, so we need to minimize the output function using the various techniques. Moreover, since the AND gate output is shared between the different OR gates, so it is also important to find the common product terms between the different functions. So by finding the common product terms between the different functions, we can use the same AND gate output for the different functions. And in this way, we can utilize the available resources efficiently. So let us take a couple of examples, and through that, let us understand it, how to use this PLA for implementing different logic functions. So let's say we want to design a full subtractor circuit using this PLA, and during the design we will use the same PLA which I have shown earlier. So this PLA has a 3 inputs, 2 outputs and the 5 product terms. So this is the truth table of the full subtractor, and as you can see, the difference output is 1 for the 4 minterms, that is minterm 1, 2, 4 and the 7, and likewise the borrow output is also 1 for the 4 minterms, that is 1, 2, 3 and the 7. So for implementing any Boolean function using the PLA, the first step is to reduce the number of product terms in the function. And if possible, then also try to get the common product terms between the various functions. So here, if we minimize the borrow output, then at the most we can reduce one product term. So earlier in the full subtractor video, we have already seen that how to minimize this borrow and the difference outputs. So for more information you can check that video. But here as you can see, after minimization in the borrow output, we can reduce at the most one product term. And if we see the difference output, then this difference output is equal to A XOR B XOR B in. That means here, it is not possible to reduce the product terms in this difference output. That means here if you see, then to implement this borrow output, we will require the 3 product terms. While to implement this different output, we will require the 4 product terms. But if you see the programmable logic array that we are using for implementing this function, that has only 5 AND gates. That means at the most, we can have only 5 product terms. So it seems like we cannot implement this function using the given PLA. But if you closely observe, then here the 3 minterms are common between the difference and the borrow output. That is minterm 1, 2 and the 7. And apart from that, the other 2 required minterms are minterm M4 and the M3. That means now the total number of product terms that we will require to implement these 2 functions is equal to 5. So now it can be easily implemented using the given PLA, which has a 3 inputs and the 5 product terms. So during the implementation, the one of the required minterm is equal to minterm M1. That is whenever both A and B are 0 and this B in is equal to 1. So here this C input corresponds to B in input. So now this term corresponds to the product term A bar B bar C. And as you can see, it is being shared between the difference as well as the borrow output. That means this product term or the output of this first AND gate will be connected to the both OR gates. Similarly, if you see the second required minterm, then that is equal to minterm M2. So for this minterm M2, this A should be 0, B should be equal to 1 and the C should be equal to 0. So now this product term corresponds to A bar B dot C bar. And once again, this product term is also shared by the 2 functions. And that is why this output of the AND gate is also connected with the both OR gates. Similarly, if you see the third required minterm, then that is equal to M3. So in the truth table, that corresponds to 0, 1, 1. So to connect this product term, this A bar is connected with the AND gate and likewise both B and C is connected with the AND gate. And now this product term corresponds to A bar dot B dot C. So this product term is only required by the borrow output and that is why it is only connected with the one OR gate. Likewise, the fourth required minterm is equal to minterm M4 and that corresponds to A dot B bar dot C bar. So this product term is only required by the difference output and that is why it is only connected with the one OR gate. Similarly, if you see the last required minterm, then that is equal to minterm M7 and that is equal to A dot B dot C. So here both A, B and the C inputs are connected with the last AND gate. And since this product term is shared between the 2 functions, so this output of this last AND gate is connected with the both OR gates. So in this way, the output of the first OR gate or the OR gate from the right one represents the difference output and the second OR gate represents the borrow output. And here in the both the functions, since we require the final outputs in the true form, so one of the inputs of both the XOR gates is connected with the logic 0. So now this F1 will represent the difference output while the F2 will represent the borrow output. So in this way, it is possible to implement the full subtractor circuit using this PLA. And as you can see over here, we only require the 5 product terms. And these are the interconnections for this AND gate and the OR gate array. So these interconnections for this PLA, or in other words, the fuse map for this PLA can be given by this programming table. So this programming table consists of the 3 sections. So in this programming table, the first section or the first column shows the product terms numerically. Then after, if you see the second section, then it specifies the required paths between the input and the AND gate. So in this product terms, if the variable appears in the true form, then in this programming table, it is marked as a 1. And if it appears in the complemented form, then it is marked as a logic 0. And in the product term, if the variable does not appear, then it is marked as a dash. So in this case, since we are using all the three variables, so in the programming table, either they are marked as logic 1 or the logic 0. So similarly, the third section specifies the path between the AND gate and the OR gates. So once again, the product term which are connected with the OR gates are marked with the logic 1, and the product terms which are not connected with the OR gate are marked with the dash. So as you can see, in both the OR gates, total 4 product terms are used, and the product term which is not connected with the OR gate is marked with the dash. So as we have seen, here we can use the output of these OR gates either in the true form or the complemented form. So if the output of the OR gate is used in the true form, then in this programming table it is marked with the T symbol. But if it is used with the complemented form, then it will be marked with the C symbol. So in this case, since both the outputs of the OR gate are used in the true form, so the one of the input to the XOR gate is connected with the logic 0. And in the programming table, it is marked with the T symbols. So this is the PLA programming table for the full subtractor. Similarly, let us see how to implement the full adder using the same PLA. So this is the truth table of the full adder. So once again, if you try to minimize the sum and the carry output of the full adder, then in the carry output, we will get the 3 product terms, that is ab.bc.ac. And in the sum output, we will get this A XOR B XOR C. Moreover, if you see, then there is a no common term in the 2 outputs. So instead of minimizing the 2 outputs, it is better to represent the 2 outputs as a sum of min terms, and it is better to find the common terms between the 2 outputs. So now, if you see the common product terms between the 2 outputs, then once again, there is only one common term. That means here, for implementing the full adder using the programmable logic array, we will require at least 7 product terms. But here, the programmable logic array which we are using has only 5 AND gates, or in other words, it can generate only 5 product terms. So we know that in the PLA, it is possible to complement the output function. So what we can do, instead of combining the 3, 5, 6 and 7 minterms in the carry output, we can combine the 0, 1, 2 and 4. So basically, when we combine these 4 minterms, then it corresponds to FC dash, or in other words, that is the inverted output. So now, if we take the complement of this function, then it is equivalent to the FC. That means here, instead of combining the product terms for this carry output FC, we will combine it for the FC dash. And if you see this FC dash and the FS, then there are 3 common terms between the 2 outputs. So here, by combining this 0, 1, 2 and 4 minterms, the output of the OR gate will be equal to FC dash. But as you know, we can complement this FC dash using the XOR gate, and effectively we can get this carry output. So that is how we will generate the sum and the carry output. So now, if you see this FC dash and the FS outputs, then there are 3 common product terms between the 2 outputs. So in total, we will require the 5 product terms. So here, the first required minterm is equal to M0, that is equal to A bar dot B bar dot C bar. So here in the AND gate, these A bar, B bar and the C bar inputs are connected with the AND gate. That means here, the output of the first AND gate corresponds to A bar dot B bar dot C bar. And this term is only required by the FC dash. So that's why it is only connected with the one OR gate. Similarly, the second required minterm is equal to M1, that is equal to A bar dot B bar dot C. So here in the second AND gate, this A bar, B bar and the C inputs are connected with the AND gate. That means here, the output of the second AND gate corresponds to A bar dot B bar dot C. And as you can see, it is required by the both outputs. So that is why this AND gate output is connected with the 2 OR gates. Likewise, the third required minterm is equal to minterm M2, that is equal to A bar dot B dot C bar. And once again, this product term is required by the both OR gates. Likewise, the fourth required minterm is equal to minterm M4, that is equal to A dot B bar dot C bar. And once again, this product term is required by the both outputs. That is why the output of this AND gate is connected to the both OR gates. And likewise, the last required minterm is equal to minterm M7, that is equal to A dot B dot C. So this minterm is only required by the sum output, and that is why it is only connected with the one OR gate. So in this way, the output of this first OR gate represents the FC dash, while the output of the second OR gate represents the sum output. So to implement this full adder, eventually we require the sum and the carry output. So here, using the XOR gate, we can complement the first OR gate output and we can generate this carry output. So for that, one of the input to the XOR gate is connected to the logic 1. So now, the output of this first XOR gate corresponds to the carry output. Similarly, the sum output is required in the true form. That is why the one of the input of the second XOR gate is connected to the logic 1. That means now, the output of the second XOR gate remains in the true form. So in this way, by minimizing the Boolean function and by finding the common product terms between the various outputs, it is possible to implement the logic functions using the PLA. So this is the corresponding programming table for this full adder. So like I said earlier, the first section or this first column shows the product terms, while the second column shows the required inputs to get these product terms. And the last column shows out of the 5 product terms, which terms are included in the output. So here, this C represents the complement. That means the output of this OR gate is complemented using the XOR gate, and this T represents the true output. So here, as we have seen, this FC dash output is complemented while the sum output Fs is used as it is. So here, for understanding purpose, a small PLA with the 3 input was shown. But if you see the actual PLA, then it has a many inputs and the outputs as well as the many product terms. So typically, the size of the PLA is specified by the number of inputs, the number of product terms in the PLA as well as the number of outputs. So commercially available PLA can have a 12 to 16 inputs, 30 to 40 product terms and 6 to 8 outputs or the OR gates. So if the PLA has a 14 inputs, 32 product terms and the 6 outputs, then it is defined as a 6 x 32 x 6 PLA. So similar to the ROM, this PLA can be a mask programmable or the field programmable. In the mask programmable PLA, the programming table is provided to the vendor during the fabrication. And according to this programming table, the vendor makes the custom PLA, which has a required internal logic that is specified by the customer. On the other hand, in case of the field programmable PLA can be programmed by the user itself with the help of the special hardware programmer. So in case of the PLA, since we have a limited number of product terms or these AND gates, so it is important to minimize the Boolean function and it is essential to find the common product terms among the different outputs. So that is all regarding the programmable logic array. So in the next video, we will learn about the another programmable logic device which is known as the PL. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.